talking about velocity dispersions in star-forming galaxies at redshifts 1 to 2.
Thank you. Does it work? So good morning, everyone. It's very nice to be back here at the Santa Cruz Galaxy Workshop. Thank you for having me. Is that okay? Not loud enough. Is that better? Can you hear me? Yes. Okay. Thank you. So I will talk today about velocity dispersions in star-forming galaxies at redshift 1 to 2. And this is work done in collaboration with Reinhard, with Emily Wisnowski, Sedona, Taro Shimizu, Natasha Förster-Schreiber. And before I come to the main topic, I want to briefly make a line to last year's workshop where I showed you some data of a redshift 1.4 galaxy where we had molecular and ionized gas measurements. We have now finished up this work. We found a central dark matter fraction of about 20% through kinematic modeling. But as you can see here on this panel, we do see a flat rotation curve. And this is because this galaxy has a particularly low velocity dispersion for its redshift, which brings me to the main part of my talk. So it has been established here in work by Susan Casson in 2012 with data from the Deep2 survey and other literature measurements, and also in follow-up work, that velocity dispersion increases with redshift. You can also see that here is a large scatter in this increase that we observe. And these enhanced velocity dispersions lead to a picture where phenomenologically, these galaxies at high redshift look very different from local disks. So we have thick turbulent disks that are kinematically hot, very gas-rich, as compared to kinematically cooler, thinner and stellar-dominated disks in the local universe. And the enhanced velocity dispersions go together with an increase in the amount of available molecular gas, shown here in a compilation by Linda Tacconi's work from earlier this year. And this, of course, also goes together with an enhanced star formation rate. So here we are at the peak of cosmic star formation at density at redshift 1 to 2, what we are looking at. And this has also been proposed as one of the reasons why we have this high velocity dispersions. Now, as I pointed out, the scatter is very high. So a concern is also here that there might be observational uncertainties involved. So what we did in the current work is that from our KMO 3D survey, we remodeled our intrinsic velocity dispersions, and then we culled from our sample galaxies with the lowest uncertainty. So this about 160 galaxies at redshift 1, 1.5, and 2, velocity dispersion versus redshift, where all those galaxies have uncertainties in the velocity dispersion that are lower than 30%. And you can see there is this decrease. We can look at weighted averages, and then it becomes a bit clearer. And now let's add some molecular data here. So here we see that also in the molecular data at high redshift, there's substantial scatter. Also, it seems that it might be systematically a bit lower, the velocity dispersions here. And also locally, you see that there's a huge scatter in velocity dispersions. We can now add some ionized gas measurements from the literature. And we see again what we already know. We have this increase with redshift, and we have a very large scatter. And this work, of course, is a huge effort by many people that have investigated this over the last years. Also, locally here, Santa Cruz very prominently. And so what we can now try to do in understanding this, we can look at models that might explain this increase in velocity dispersion with redshift. And a very successful model in this context is that of looking at high redshift disks as marginally tumor stable disks in the context of an equilibrium model where star-forming galaxies are described as being in a quasi-stable equilibrium between inflows from the cosmic web, star formation rate, and outflows. And this leads to a connection between intrinsic velocity dispersion and rotation velocity and gas fraction. And also in our clean data, this is indeed still the strongest correlation that we find. Also, I should point out that the prediction from this model that has been featured in Emily Wisnowski's 2015 paper predicts velocity dispersions at high redshift that are a bit higher than what we observe, and this is probably due to the culling of data that we do, where we remove dispersion-dominated galaxies at a higher redshift. Now, a different way to investigate the increase in velocity dispersion is to remove the redshift dependence and then just look at correlations of the scatter with different properties. So what I show here on the y-axis, we have the velocity dispersion, and this is now normalized to its mean value at a given redshift bin. So the 0 line is basically the main trend of increased velocity dispersion, and then positive values are higher dispersion galaxies, and negative values are lower dispersion galaxies. This is colored in redshift, so blue points are low redshift, red points are high redshift galaxies, and here I show this against inclination. We do not see a correlation, which makes our life easier in this context. And then one could naively expect correlations with, for example, gas mass surface density, Sedona already mentioned, star formation at surface density in the stellar feedback-driven idea. And we looked at very many of these properties. We could not pin down, also not with enhanced statistical methods like principal component analysis, a very clear correlation of the scatter with any property. However, we found somewhat weak correlation with main sequence offset here. So you can see that there is maybe a slight trend. So this suggests that in very extreme environments, like starbursting galaxies, the feedback might have some, contribution to driving this turbulence. But at most, this is a very weak trend, and you see that the scatter is still very large. So gravity comes to our rescue. I'm showing here the latest models from Mark Krumholz. This is intrinsic dispersion versus star formation rate. In gray, I show here local data. Red points are high redshift data, and the yellow points are our K-3D and SINS best sample at the moment. The red line here is Mark's high redshift model. So this is classified as with galaxies with a certain rotation velocity, which is about 200 kilometers per second here. Most of the gas is assumed to be in the molecular star forming phase, and the gas is also assumed to have a very large contribution, more than 50% to the gravitational self-gravity of the disk. And you can see that this model that is shown here on the left side, which is a combination of internal transport and feedback, does a very good job in catching here the trend that we see of the increased dispersions. And of course, these ideas that the velocity dispersion is driven by a galaxy-wide release of gravitational energy through clump formation migration, radial inflows, or accretion from the cosmic web, has been investigated over the last years, also by a lot of people here. Avishai, Daniel, and Nia have done a lot of work in this context. And what I want to emphasize here is that if we look at a model that does not include these gravitational instabilities, these transport modes, but only stellar feedback, then we get a line that is above, around here. So these galaxies that use only star formation feedback in trying to explain the high velocity dispersions cannot explain the very high values that we observe at high redshift. And this has also support from observations. So I'm showing here just a few examples. We see that we have gravitational unstable clump formation. We have radial inflows that we can detect in residual maps of velocity fields, for example. And we heard yesterday also about gas accretion. So before I finish, I want to briefly show a plot from this paper by Hung and collaborators, which is on the archive. They investigate the fire simulations. We see here 3 different galaxies over cosmic time. The left axis shows the velocity dispersion. So what they find through cross-correlation in their models is that after gas accretion events, which are the dashed blue lines here, this is very often followed by an enhance in the intrinsic velocity dispersion. These are the red lines. And then sometimes this is again then followed by enhanced star formation rate, which is the light blue dashed lines. And what I want you to note here is that we see this huge time variability of the dispersion on timescales that are very short for us observers. And I think this investigation of the simulations here is a nice support for the gravitational disk instability idea, which also suggests that we are not necessarily looking at galaxies that have intrinsically very different properties when we look at galaxies that are scattered in dispersion values, but that we might just look at galaxies at different point in time, which basically can all, after a short amount of time, maybe reach a different value of the dispersion that we then observe in the population average. So I want to conclude with, we have now tried to investigate with a very carefully culled sample the redshift evolution of the velocity dispersion. We still find that there's large scatter, so this is not just observational uncertainties. We believe that this is real. And also there is indication that stellar feedback might be important in driving some of the high redshift turbulence. It has become clear that gravitational effects such as the disk instabilities, clump formation, migration, radial inflows are really necessary and are the dominant mode at high redshift to explain these turbulences. Thank you for your attention.
Avishai.
I would like to add to this last point, last figure, that on top of this feedback and disk instabilities that drives inflow within the disk, there's a third mechanism which drives turbulence, and that's the inflow itself, the cosmological accretions through streams and mergers and so on, which drives turbulence. And I think the challenge now, after this nice Krumholz et al. Paper, to try to put all those three together. And that's what we are trying to do. But I'm sure it will be another important contributor to the dispersion.
Looking forward to these models.
Actually, there was a paper I wrote a while ago with Shai Genel on this, but without the feedback. Yeah. So we have to put all the three together.
Kevin?
Can you say something about the physical scales for this turbulence, both from the data and from the theoretical models?
Yeah, so if you look only at feedback, then you could explain turbulences of maybe 20 to 30 kilometers per second or so. If you include these gravitational terms, you can see how this really goes up to values that are much larger than what we observe in galaxies that are not dispersion dominated. So these are not shown here. If we add dispersion dominated galaxies, then we can also go up to maybe 200 kilometers per second or something. I should also point out that what Mark does here is that he corrects a lot of the observational data for thermal broadening in H2 regions. So he assumes that these are about 15 kilometers per second or so. And locally, these corrections would be maybe 5 to 9 kilometers per second. Does that answer your question? The length scales. Yeah. Sorry? So it depends a bit on the tracer that you look at. So for the ionized gas, this, of course, is connected to H2 regions and gas that is close around that. So you would expect maybe that the molecular gas does not have these high turbulences, and this is what you see in the systematic offset that is probably observed at the higher redshifts. So what Avishai just said is, of course, that it has to be somewhat connected to the disk scale heights that we see of several hundreds of parsecs that are needed to puff up these disks. So if it goes beyond that, then this would probably already go into an outflow or so. But it's very hard to make very precise measurements of this at high redshift. We are trying also to do this with stacks of H-on galaxies to pin down really the scale heights, but this is very challenging.
Okay, thank you, Hannah. Our next speaker is James Wedsley, talking about